So this is the M2 Pearson's Edexcel Jan 014 paper we're going to do. First question is standard, well, for A is at least, standard impulse question. Impulse is change in momentum, or that, we can write it like that. We're asked for the impulse, and the initial velocity is this, and the final velocity is this, and the mass is 2. So that's 2I minus 3J minus 3I plus 4J. And that's all times by 2. So that equals to minus 2I, and it's minus 14J. Do be careful though, the question is asked for the magnitude. If it just asks for the momentum, momentum's a vector quantity, so there it is, but it asks for the magnitude. So the magnitude of that is the square root of 2 squared plus 14 squared. So that's the square root of 200. Which is equal to 10 the square root of 2 newtons. We are allowed to leave it like that, but it might be cautious to also give 3 significant figures. And to 3 significant figures, it's 14.1 newtons. Doesn't do any harm to do that, although absurd is almost would normally always be accepted in these questions, I think. Question B, a little bit fiddly. It's about angles. You need to read it and interpret. The angle between the direction of the impulse. Well, this is our impulse here. And remember the direction, it doesn't matter if, you know what the scale is here. It's going 2 here and 14 here, or 1 and 7 for that matter. Down 1. It's going in that direction because of the 2 negatives. And then with the velocity before, so that's going to go upwards like this. Okay, so we want the angle in between those two. Just to pull it down a bit. So we want the angle in between those two there. Okay, well, let's just draw a diagram for this. Okay, and we want this whole angle. And notice here, because we're talking about vectors, we need to make sure when we're talking about the angle between 2 vectors that the 2 arrows, you'll see this in C4, have to go apart against each other like that. So we have this angle here, using just normal trig, is tan minus 1 of 1 over 7. This angle here is, because it's 4 up and 3 across, is tan minus 1 4 over 3. And notice this is a right angle. So the required angle is going to be equal to the tan minus 1 4 over 3 plus tan minus 1 1 over 7 plus the right angle here, 90 degrees, and that's going to give us the angle 151 degrees. Okay, so that is question 1 done. Let's have a look at question 2. Scroll through that first. Okay, these are normally often quite nice questions. The function's relatively simple. Got a quadratic function for v. So v, if we were to ask for a velocity, hasn't asked for it, but if we were asked for a velocity time graph, it would do something like this. That's good. I'm going to refer back to that in a moment. But let's just do part A first, which is really quite straightforward. We do need to multiply it out. So that equals to 3t squared minus 16t plus 20. So the acceleration is that differentiated. So dv by dt, which is the acceleration, is equal to 6t minus 16. We want the acceleration when t equals to 3. So that gives acceleration is 6 times 3 minus 16, which is 2 meters per second squared. Okay, so that is the answer to the first part, nice and straightforward. Now part B, we need to be careful because as we go, it says for the first 3 seconds, and it's talked about a distance, and there is a difference between distance and displacement. Often the answer will be the same, but not here, because as you notice, as for over the 3 second period, we've got a change of direction. Velocity is it's basically started to go backwards from here. So we really do need to be careful, because what's going to happen is it's going to go forward for the first 2 seconds, and then it's going to go backwards for a little while. Okay, I'll refer back to that sketch in a moment. So let's just work out the displacement, which is the velocity integrated. So that's 3t squared minus 16t plus 20 dt. That equals t cubed minus 8t squared plus 20t plus c. Now c is equal to 0 here, because when s equals to 0, t equals to 0. It's often implied in the question, but here it's made it implicit, that by saying it starts at the origin, so that gives us c equals 0. So we have s is equal to t cubed minus 8t squared plus 20t. Okay, that's our expression for s. We're going to use that expression when t equals to 2 to see how far it's got, because as we can see from here and here, the velocity is 0 at 2. So let's see what the displacement is before it changes direction. So, because that's basically, that's going to be whatever this distance is here we're working out. Okay, so that will be 2 cubed minus 8 times 2 squared plus 20 times 2. And that equals to 16. Let's work out when t equals to 3. We have s is equal to 3 cubed minus 8 times 3 squared plus 20 times 3. And that equals to 15. So, what does this mean? Basically, hopefully you've got the idea now, this distance is 16, the displacement, but its distance is 16, and this distance here is 15, which of course means that this distance here is 1. So it's basically gone here and back again. So the distance travelled is those two numbers added together. So the distance is equal to 16 plus 1, which is equal to 17. Okay. Now on to part C. Now the key word here is never returns to 0. Doesn't say that it's never at 0. Of course it's at 0 at the beginning. Well, let's look at our displacement formula again. That's t t squared minus 8t plus 20. Obviously, this bit is at the beginning. T is obviously, so this is it will return, if this is equal to 0, will return if and when t squared minus 8t plus 20 equals 0. But this is where a bit of completing the square would help. T squared minus 8t plus 20, if we complete the square of that, half the 8 gives you 4. That basically is equal to that. But that's greater than 0. So that basically means that it will not return. Because t squared minus 8t plus 20 is never equal to 0. Okay, and that's that question done. So question 2 wasn't too bad, quite nice. Part B had to check the displacement thing, but pretty okay. Let's have a look at the next question. Scrolling a few blank pages first. Okay, looks like a standard, well, power question. Let's have a look. Okay, first part is talking about, well, it's quite a lot of marks here, so I suspect we're going to have to sweat a bit for it. But it says it's on straight horizontal road, it's got constant resistance, and it's going at constant speed. Okay, so we've basically got something going along a straight road with some driving force with constant resistance, and we've got the velocity is 30 and the mass is 550. Okay, now let's just first of all, because it's constant velocity, we can say that F is equal to R, because it's in equilibrium essentially. Forces are balanced, so F is equal to R. We can also use P equals FV, because the velocity is 30, so we can say the power, which we're not given, is equal to 30 F. But F is equal to R, so that also means that the power is equal to 30 R. I think I'm going to be using that later. Okay, because we haven't actually got anywhere with answering the question yet, but it'll come. It then starts talking about it travelling up a slope. Travels up a line with this angle and then with this speed, because of course it's working at the same power, which must mean that it's reducing its speed. So now this time, I'm going to mark that on as F, but so long as we understand that the F is going to be different. But because I know I'm not going to be using this F again here, I don't think it matters. So this angle's theta. So if we use the fact that it's going at constant velocity and use P equals to FV as well. So P equals to FV again, that's saying that P, oh, that's not really telling us much at this stage. We just know that P is equal to 25 F. Right, so it just shows you that this F can't possibly be, these two F's can't possibly be the same. Put a dash on it or whatever if you don't like that. But as I say, I know I'm not going to use this again. So P is equal to 25F. We've got the constant velocity, so the forces are balanced. A is 0 basically. So we can talk about forces upwards being equal to forces downwards along the slope. Let's go parallel. So we're going parallel to the slope. So we've got F going upwards, and then we've got a component of a weight, mg sine theta, going downwards. And also downwards is r, which in this case is the same as it was before. That's equal to 0. So F is equal to mg sine theta plus r. But we do know m, that's 550. We do know g, 9.8. Sine theta is 1 over 14 plus r. That breaks down to F is equal to 385 plus r. So now let's just use that in here. So we're going to sub for F. So we have P is equal to 25 times 385 plus r. Now the power, it's been working at the same rate, so we've got these two equations that we can solve for P. So if we just equate those two, we have 25 385 plus r is equal to 30 r. So that gives us 25 times 385, 9625, plus 25r equals 30r. So that gives us 5r equals 9625. So r equals 1925. Would be penalised for writing 1925 or not rounding here. The rubric really is 3 significant figures is pretty well always accepted. Here 2 significant figures would be preferred because G is involved, which is given to 2 significant figures. So we can say that's equal to 1,900 newtons to 2SF. Okay, 2SF is not normally good enough, but it is here because of the G. Okay, now that's the first part done. Part B, I haven't worked out P yet, so let's just do that. P is equal to let's use the 30R, 30 times 1925. And I'm going to round that to 3 significant figures as well. So it's 58000 watts is the power. So now we are on to part B. Okay, it says for part B, let's just tidy this up for a sec. Okay, so that's better. It says find the acceleration when it travels along so we're back along a straight road again. When it travels, and the rate is different. I've got a different F again, but again, because the 2 values of F before are not going to be used, I'm not going to bother relabeling it. And R is still the same, and we know that R is 1925. So again, it's almost the same thing. Use P equals FV and F equals MA in this case because there is acceleration parallel to the slope. So P equals FV. We've got 50,000 is equal to the force times velocity. We are told the velocity is 20. So that gives us F equals to 2,500. So using that in F equals MA, that's going to give us 2,500 minus 1925 is equal to the mass of this thing, which is 550, I think. Let's just check. 550, yes. Times by the acceleration. Okay, if we work out A there to two significant figures, that's going to give us A is equal to 1.0 meters per second. You are also, okay, given three significant figures, which would be 1.05 meters per second. Okay, so let's go on to the next question. Scrolling through the blank pages again, there's about 4 of them. Okay, centres of mass, these are often quite tricky, so we'll hopefully have to take it slowly. Right, we've got one of these kind of composite shapes with almost a bit cut out of an equilateral triangle. We're told that the centre of mass of the whole shape is at D, here. So we're going to need to use that fact. Let's just work out some areas first of all. Let's just do it. Let's just talk about the areas or ratio of masses, because they're all in because it's uniform. The area will work in terms of the ratio of masses. Let's talk. We've got the triangle ABC. This triangle here. Well, let's just look at this distance here. That distance there is equal to 2 the square root of 3. You can use Pythagoras or trig to work that out. It's basically 4 cos 30 or 4 sine 60, one or the other. Okay, and this distance is 2. So the area of one of these triangles is going to be equal to 2 the square root of 3. So the area of the whole triangle is 4 the square root of 3. Now the area of half this triangle, because this length is 2 the square root of 3 and this length is 2. That's the area of one of these, but we've got 2 of them. So that's doubling that, so it's going to make it 4 the square root of 3. Or you might have used half A, B sine C, I suppose, but whatever. We've got the area is 4 the square root of 3. We've also got a triangle, let's change the colour back to blue. We've also got the triangle ADC, which I know that this is a bit cut out, but we just must make sure we put a negative sign in our formula. But so the triangle ADC is equal to a half times 4, which is 2, because this length here is 4. So that's 2h. Obviously the composite shape, which is the kind of arrow shape there, which is A, B, D, C, is going to be the difference between those two, which will be 4 the square root of 3 minus h. Okay, now minus 2h, of course. Okay, minus 2h. Right, so that's the masses. The distance, centre of mass from base distances. I should say also at this stage we really are only dealing in one dimension. We know that our centre of mass lies along this line here, so we're really not worried about split it, x and y's or whatever. It's all from the base here. Right, so the triangle, the equilateral triangle, well, as I've already said, this distance here is 2 the square root of 3. So the distance will be a third of that, so that's 2 to the square root of 3 over 3. Let's write that in there. 2 to the square root of 3 over 3. Okay, and then obviously the one of this one is just h over 3. H over 3. And we are actually told, this is where I did say we were going to use this fact, the centre of mass is at D, because the centre of mass of the composite set, the whole thing together, is placed at D. So that means that's H from there. Okay, so right, now we can use our moments equation, our sigma mi xi is equal to x bar sigma mi equation. But we do need to take care because this bit here is taken away, this bit is cut out a bit, so that we're going to make that negative. So that's 4 to the square root of 3 times 2 to the square root of 3 over 3. Minus 2h times h over 3 equals h times 4 the square root of 3 minus 2h. Okay. Multiplying the first term together, the square root of 3 times by the square root of 3 is 3. That's going to cancel with the 3 on the bottom, so that's 8. This is equal to 2h squared over 3. This is equal to 4 the square root of 3h. And this is equal to 2h squared. Okay, let's times everything by 3 at this stage. So we have 24 minus 2h squared is equal to 12 the square root of 3h minus 6h squared. Take everything over to the left hand side and that becomes 4h squared minus 12 the square root of 3h and plus 24 equals 0. Bit of a strange looking code, well it's not that strange but it's got a surd in it. So well, let's divide through by 4. That's h squared minus 3 the square root of 3h plus 6 equals 0. Let's tidy this up a bit now. Okay, that's better. Going back to the question, it says show that h equals the square root of 3. Now I'm going to cheat it, well it's not really cheating, but I'm going to use the fact that we're asked to show that, to factorise. We can use the quadratic formula if we want. But I'm going to do this because if square root of 3 is a solution, then we should have a bracket h minus the square root of 3 here. And then that means on this one, in order to get the 6, I need to have that 2 the square root of 3 here equals 0. So we've got h equals the square root of 3 because h is not equal to the 2 the square root of 3. It has told us that h is less than 2 the square root of 3. It'd be impossible because remember 2 the square root of 3 was all the way up here. So that wouldn't work. That would make the centre of mass up there, which basically means you're cutting the whole damn shape away. So obviously that's not appropriate. So this is the one that we want as required. Okay, so we've got the. I think we've got a slightly tricky aspect coming now. It now says that the weight of the lamina ABCD is freely suspended from A, from here. Now you'll see if you suspend it from A, it's obviously going to start. D is going to lie below A. But in this case, it's saying it's going to actually, a force is going to be applied to make AB horizontal. But A would have to be above B here. So I'm going to just draw that. A is going to have to be horizontally above B. Let's draw an equilateral triangle. And it says that it's being suspended from the point A, so by a rope or hinge or whatever. So we have our shape here. Now I haven't actually shown the cut out bit, but let's just go. We've got A, B, and C. Okay, so in fact what's happening here, we've got AB horizontal like that, and in fact we've got the thing cut out like this. Not particularly good diagram, but in most of these situations, this is a bit awkward, because if you actually, normally in these kind of situations, I think it's best to draw a horizontal and vertical line on here, like on the diagram here, but in this case it's kind of difficult to actually makes it more difficult. So something like that. And we've got the centre of mass is here. Let's draw that on. Okay. Now we've got the centre of mass is here. Now what do we know here? Let's have a look. We know that this length from here to here is the square root of 3. Why? Because this length is also the square root of 3, and the whole thing is the square root of 3. So that the distance there, AD, is the square root of 3, because that's where the thing's hanging from. Now, I haven't actually even mentioned the question yet. It says that there's a horizontal force at B, and they've called it F. Okay, and that the weight of the whole thing is W. Right, so it needs to be in equilibrium. Oh boy, so it's a bit tricky. If we take moments about A, let's just mark some things on the diagram here. We know that this angle here is 30 degrees. Okay, we know, so we want this distance here is the perpendicular distance from the weight, from the line of action there is a perpendicular distance. That's the distance we're looking for. And we also want this distance here, which is pretty easy, that's 4. So if we take moments about A, we have that equals to, it's the clockwise force is the 4F. That's equal to W times by this distance here. Now using this distance here, using that's the square root of 3, which is this distance here. Okay, and yeah, so that's the distance from here to here, square root of 3, and that's going to be square root of 3 sine 30. Let's go back to blue. Sine 30 is equal to half, of course. So that's telling us that F is equal to W, the square root of 3 over 8. Okay, so that is the answer to question 4. I thought that question's a bit tricky, a bit fiddly, because the diagram is quite hard to do. Normally with these questions we can just work with the, mark on a vertical line and horizontal, so we could have called that the vertical. I suppose it is possible, but I'm not sure if it actually helps. And this would be horizontal, and we're suspending it, looking at it upside down. We'll be looking at that distance, and then whichever way you do it, it's quite confusing. So even if you try and adapt it, your diagram that you've got, it's actually